Good morning, everyone. Today we will see Hamiltonian cycle using backtracking approach. How we can solve Hamiltonian cycle problem using a strategy called backtracking. First, we will see what is Hamiltonian cycle. Hamiltonian cycle or circuit in a given graph G is a cycle that visits every vertex exactly once and returns to the starting vertex. See the given graph contains collection of vertices and edges. V represents vertices and E represents edges. For the given graph, the starting node is A. So from the starting node A, we should visit all the nodes exactly once. And from the last node, there should be a path to the starting node. Here, starting node is A. The starting node is not given. If graph contains label alphabets or numbers, we are taking the minimum node, minimum value, minimum alphabet or minimum numeric value as a starting node. Here we have the order A, B, C, D. So take A is the starting node. So from the node A, visit the node B. From B, visit the node D. From D, explore to C. Now A, B, D, C. All the nodes visited exactly once. And from the last node C, there should be a path to the starting node A. That is called a Hamiltonian cycle. Starting node and the ending node is same. In between these two, remaining nodes should be exactly added only once. That is called Hamiltonian cycle. We are going to build a Hamiltonian path by using backtracking approach. By visiting nodes one by one till all nodes are explored and from the last reach the starting node. That is called Hamiltonian cycle. And how we can solve Hamiltonian cycle problem using backtracking. So we know what is backtracking. The starting node is A. From the starting node or initial solution, explore all the possibilities. Explore all the options. And that is level 1. From the level 1, explore remain all the possibilities from the level 1 to level 2. Like that, all levels are explored, all possibilities are explored in a backtracking approach till we have a solution. If you are moving in one path, that node cannot be able to proceed to the next level, does not lead to a solution, that is called dead end. So if we reach the dead end in Hamiltonian cycle, then move back to the previous node and explore remaining possibilities. If we reach a dead end, we backtrack and try different vertex. So this type of problem can have zero solution or more solution. For some problem, there is no solution. For some problem, we have more than one solution. And if a graph contains Hamiltonian cycle, it is called Hamiltonian graph. Otherwise, not a non-Hamiltonian graph. What is Hamiltonian path for the given graph? So there's a starting node. From the starting node, visit all the nodes exactly once. That is Hamiltonian path. What is Hamiltonian cycle? From the last node in the Hamiltonian path, it should reach the starting node, starting vertex. So Hamiltonian path is open. It's not a cycle. Starting at one node, visit all the nodes exactly once. That is Hamiltonian path. From the Hamiltonian path, we can derive Hamiltonian cycle by taking the last node, visit the starting node. That is called Hamiltonian cycle. And we will see what is backtracking concept. It's a one type of problem solving method. This type of problem have multiple possibilities or multiple options. The problem can be explored with multiple options. If one option does not lead to a solution or valid to proceed further, we can stop at the level, then move back to the previous node, we explore all the possibilities. So this is called backtracking approach. So the path does not lead to a solution is called dead end. So in the dead end, backtracking concept is applied, move back to the previous step. Or if we reach the solution also, we can go back to the previous node, we can find for another solutions. Here, in the backtracking concept, if we are having one solution, we are not going to stop. We are trying to find multiple solutions. We are trying all the possibilities. That is called backtracking. The current possibility lead to a solution is called solution end. The solution is returned to the user. Then other possibilities are explored to find another solution till all possibilities are explored. This is called backtracking. And what are the steps in backtracking? Backtracking process can be represented in the form of state space tree. We know what is tree. Tree has a root node and it has a child node. The nodes are represented in a hierarchical structure. That is, it includes parent-child relationship. And how we can represent the execution path of backtracking using state space tree. So we have the initial node. That's a root node. Root node is the initial solution. From the initial solution, explore all the possibilities to find the next level. Explore all the possibilities for the root node to go to the next level. Then from the level 1, explore all the possibilities to go to the level 2. If the current path leads to a solution is called solution path. Return the solution. If the current path does not lead to a solution or optimal solution or is a valid solution called dead end. So stop the process, go back to the previous possibility and find another option. This process is repeated until all possibilities are explored. So finally, return the state space tree with zero solution or one solution or multiple solution. So this is called backtracking. Backtracking problem can have no solution or can one or multiple solutions. So we are checking all the possibilities from one level to another level. This is called backtracking approach. And what is state space tree? The process is represented in state space tree. So tree contains set of nodes. Edges contains a path. So root node is a initial solution. From the initial solution, go to the next level. Explore all the possibilities. Get the level 1 nodes. From the level 1, explore all the possibilities to go to the level 2. So the problems can be solved in multiple levels. So at some point, at some node, not possible to expand. It's not possible to explore. It can be a solution or it cannot be a solution. If it is a solution, the path from the root to the current node is a solution path. If the current node does not lead to a solution, that is called dead end. So move back to the previous, find another options. So what is promising node, non-promising node? If the node in a state space tree leads to a solution, that is called promising node. If the node does not lead to a solution, that is called dead end or non-promising node. The node does not possible to explore to the next level to find a solution is called non-promising node. In the case of state space tree, root node is initial solution. The leaf nodes are either solution or dead end. Intermediate nodes are intermediate solutions to the problem that can be explored to the next level. So there are 3 types of nodes. Root node is the initial solution. Intermediate node, there is intermediate solution. And the last node level, that's a leaf nodes are either solution or dead end. And see the example, there are 6 vertices A, B, C, D, E, F. This is a state space tree. It's a part of state space tree for the given graph. It's not a complete state space tree. We are taking only one adjacent node of A. First, we have to find the adjacent node for all the nodes. For A, what are the adjacent nodes? Adjacent node means neighboring node. Neighboring node for A. So for the node A, B, C, D. So we have to find the adjacent node. List out in alphabetical order. B, C, D. So we are taking only B. In this example, I am taking only B adjacent node. So for A, B is adjacent node. And also two more trees should be added. That is C, D. I'm taking only the B for explanation. So B is adjacent node for A. Then take B, the next level, node 1. Then B can be explored to the next level. So what is the adjacent node for B? ACF. See the graph? ACF is adjacent node for B. So see the path A is already visited. If it is already visited in the path, we should not visit again. So we have to add only unvisited node in the path. So for B, C and D is C and F is adjacent node. So C is a left child, F is a right child. Now we will see first C. What is the adjacent node for C? There are four adjacent nodes A, B, D, E. So see the path AB is already visited. For C, AB is already visited. Unvisited node is D and E. So add unvisited node D and E. So add it in alphabetical order. D is left child and E is right child. And for the D, now expand D. Node number 3. For D, what the adjacent node for D? A, C, E. See the path A and C is already visited. So unvisited is only E. So add to the node D. Now we are in number 4, E. So take the node E. What is the adjacent node for E? C, D, F. See the graph adjacent node E is C, D, F. So C is already visited, D is already visited, and is already added in the path. So left out is F. So add F to the node E. Now see the path leftmost 0, 1, 2, A, B, C, D, E, F. All nodes are visited exactly once. This is called Hamiltonian path. What is Hamiltonian cycle? From the last node, there should be a path to reach the starting node. That means for the last node, A should be the adjacent node or neighboring node. For F, A is not neighboring node in this diagram, the graph. So this is called dead end. Why it is dead end? Even though all nodes are visited, there is no path from last node to starting node A. So it does not form a cycle. So this is called dead end. And move back to the previous E, D, C. Then find the adjacent node of C. Adjacent node for C is A, B, D, E. See the path A, B is already added, D is already added. So now we are adding E. Node number 6, E to the node C. And now for what the adjacent node for E? For E, adjacent nodes are C, D, F. See the path C is already added. Left out is D and F. Add the node D and F. Now, node number 7 for the D. What is the adjacent node for D? A, C, E. See the path already visited. A, C is already added in the path. So we can't add it. We are not able to explore further. But it's not a solution because all nodes are not visited. A, B, C, D, E, F is not visited. So this is not a feasible solution for Hamiltonian cycle. So that is called dead end. Not possible to export to the next level. And also it's not a feasible solution also. So move back to the previous step. Expand another option. See node number 8, F. Adjacent node of E is F. For the F, see the path A, B, C, E, F. D is missing. D is not visited. Okay, so it is also dead end. Again, move back to node number 6. Again, move back to node number 2. Again, move back to node number 1. Then go for the next option, that is node number 9. What are the node for B, C and F? C is completed. Now we are going to node F. From the F, what is the adjacent node for F? B and E. So B is already visited. Add only unvisited node E, node number 10 to the node F. Then from E, what is the adjacent node for E? C, D, F. So C is unvisited. So we can add C. So only one node can be visited at a time. C. Then from C, what are the nodes can be visited? A, B, D, E. So A is already visited, B is already visited, E is already visited. So unvisited node is only D. So D can be visited from node C. That is node 12 can be visited from node number C. And see the node number 12, D. See the path A, B, C, D, E, F. All 6 nodes are added once. Yes. And from the D, there should be a path to add a to reach a starting node A. Yes, A is adjacent node for D. See the graph? There's a path from D to A. A is adjacent node for D. Now form a cycle. See the square? That is a starting node. Root node. Root node is A and the solution path, the last node is A. So starting node is A. All nodes are visited exactly once. B, F, E, C, D. Then from the last node, there's a path to reach the starting node A. So this is called Hamiltonian cycle. It's a complete path. Starting node to all the nodes added exactly once. Then from the last node, there should be a path to reach the starting node A. So this is called Hamiltonian cycle. The label is solution. See the state space tree. Leaf nodes are labeled with either dead end or solution. So the problem has one solution, and also we can explore two more branches. We can get another solution. And we will see what is state space tree. State space tree is a representation of execution of backtracking algorithm. We are representing all the possible states and how it can be explored. What are the solutions? What are the dead end? All components are represented in state space tree. So it has a root node, intermediate node, and leaf node. Root node is initial solution to the given problem. And the that is intermediate nodes are intermediate solutions that derived from the root node. And so intermediate nodes can be explored to the dead end or solution end. So leaf nodes represents either complete solution or dead end. So leaf node leaf node cannot be expanded further because it is a dead end, not feasible, or it can be a solution. And what are the operations we can perform with the state space tree? Expansion. So we can go level by level. We can expand the nodes from one level to another level, from root to level 1 to level 2, level 3. So we can expand, we can explore all the possibilities. And what is backtracking? If we reach the dead end or any solution, to check all the possibilities, we move back to the previous options or possibilities, then exploring all the possibilities. That's called backtracking. And pruning. Pruning is ignoring certain branches based on constraints. There is optimization. To avoid the extra calculations or computations, we can prune some part of the work or part of the state space tree to save the time to reach the optimal solutions. That is called pruning. And see the graph. uh, G is a graph. It contains 4 vertices and 4 edges. Now, by default, starting node is A because it's labeled with alphabets. Minimum alphabet is A. So, starting from A, I can go to B or C. There are two options. Yes, I am going to A to B. Then B to D, D to C. Now, A to B, B to D, D to C. This is a Hamiltonian path. All nodes are visited exactly once. Then, for the last node C, there's a path to reach the starting node A. So it is one Hamiltonian cycle. Another choice is I can move this way. A to C, C to D, D to B. This is called Hamiltonian path. From B, there's a path to reach A. So it's another Hamiltonian cycle. This graph contains two Hamiltonian cycle, A, B, D, C, A and A, C, D, B, A. So starting and ending node should be same. All nodes are visited exactly once except the starting. And second example, so these type of problem have 0 or more solution. Some problems have no solution. See the graph. I'm starting at node A. So from A, I can move to D, D to C, C to B, B to E. This is Hamiltonian path. A to D, D to C, C to B, B to E. But from the last node, there is a no direct path to starting node. E to A not possible. So this problem has no Hamiltonian cycle. The C is called articulation point that divides the component into two parts. So if graph has articulation, it has no Hamiltonian cycle. So this problem have no solution. It has Hamiltonian path, but it has no Hamiltonian cycle. See the next example, the graph G, V comma E, that is there are 5 nodes. So it has two Hamiltonian cycle. See starting node A, B, C, D, E, then again to A. And another option is A to E, E to D, D to C, C to B, then A. So starting and ending node is same, except the last node, all nodes are added exactly once. That is called Hamiltonian cycle. And this one, we will see an example. Find adjacency matrix for the given graph. How we can solve? We can see the example. So how we can generate adjacency matrix. So there are 5 nodes. We can form a 5 cross 5 matrix. A, B, C, D, E, then A, B, C, D, E. The adjacency matrix has two values, 0 or 1. Either 0 or 1. 0 means there is no path. 1 means there's a path. That means it's adjacency node. 1 means adjacency node, there's a path. 0 means no adjacency node, no path. For example, self node A to A 0 and C A to B, there's a path. So A to B value is 1. Then A to C, there's no direct path from A to C, the value is 0. Then A to D, there's no direct path from A to D, the value is 0. Then A to E, there's a path, so 1. Like that, we have to fill all the matrix. There's a path, assign 1, otherwise 0. Okay. Now, take the root node A. See the state space tree. Root node is A. There's an initial solution. There's a state space tree initial solution. For A, there are two adjacent nodes, B and E. See the matrix for first row for A to B and A to E. The value is 1. That means it has two adjacent nodes, A to B, A to E. So take A to B and A to E. Now take the first visitor node B. From B, for the B, see the adjacency nodes A, C, D. See the second row for B, A is 1, C is 1, D is 1. So add C and D. Now take D. For D, B, C, E is adjacent nodes. So already B is visitor and add the node C in the path. Now from the C, node C, for the node C, B and D is adjacent node. So already added in the path. B and D is already added in a path. So this is not a feasible solution. This is called dead end. It is not possible to expand to the next level. Again, move back to the node D, move back to the B, then find the next choice C. For the node C, what are the adjacent nodes for C? B and D. So B and D is adjacent node for C. So B is already added, visited. So unvisited is D. Add D to C. Then what are adjacent node for D? For D is adjacent node is BCE. So BC is already added. We can add E in the path. For the E, now see the E, A, B, C, D, E. All nodes are added exactly once. Then from the node A, there's a path to A. For the node E, A is adjacency node. See the last row for E, A. For E to A is 1. That is A is adjacency node for A. So it forms a cycle. Starting A and ending A. All nodes are added exactly once. This is also solution. And move back to the root node, find another options. That is E is adjacent node for A. Then find out the adjacent node for E, that is D, then BC, then move back to the previous, then CBA. It's another solution. So this problem has two solutions, A, E, D, C, B, A and A, B, C, D, E, A. So it has two solutions. State space tree has leaf node. Leaf node is labeled with either dead end or solution. So it has two solutions, that is Hamiltonian, path and cycle. So A to B, B to C, D to E, E to A. This is called Hamiltonian cycle. And what's time complexity? T of n is order of n factorial. So this is a factorial time complexity because backtracking tries all the permutations for n vertices. Each recursive call explores n minus 1 possibilities. For remaining vertices, n is the number of vertices. So for n minus 1. For n minus 1, n minus 2. n minus 2, n minus 3. It repeats till we have a single node. In the worst case, the algorithm tries all possibilities permutations of the vertices to find a valid cycle. So there are n minus 1 factorial possible sequence of vertices. So the time complexity is order of n factorial. For each subsequence, it checks the edges exist between consecutive vertices finally from the last back to the first. The time complexity of Hamiltonian cycle is n factorial because it checks all n minus 1 combinations. Then, what is the space complexity? S of n equal to order of n. Path array takes order of n space and recursion stack also uses order of n. So, space complexity is order of n. Thank you.